All right, thanks. Thanks for inviting me. This is great. I just wanted to talk about sparse data in scientific imaging applications. Let me bring up my pointer because otherwise I can't see it, I think. Okay, so I work at a place called the Molecular Foundry, which is a knowledge-based user center in Berkeley, California, where we do a lot of nanoscale research science. And basically, the facility has almost anything you want in order to do nanoscale research. And I specifically work on something called transmission electron microscopy. So what is that? So this is a transmission electron microscope. It's a big big microscope in a box. This is about 12 feet tall. And you have an electron source in it. You have a whole bunch of lenses before the sample, which is about in the middle. Then you have lenses on the other side in order to magnify the beam or the image. And then you have a detector on the bottom. And we can have detectors of all different types. And today I'm going to be talking about a new detector that we have where we have this very big problem, very big data sets. So these are some of the data sets that you can get. We generally work with images. So we can look at nanoparticles where each one of these dots in the image is a column of atoms that you're looking down. So you're projecting through the object, kind of like if you ever take an X-ray of your teeth or your hand, you get one picture, but it's going through your entire thing. So we do the same thing, but we can do it at atomic resolution. So you can look at nanoparticles, the atomic structure of nanoparticles embedded in things. We can look at new materials like gold nanoparticles that are embedded in a block of polymer that self-assemble into these interesting motifs. You can put single layers of atoms together to make new materials like superlattices, where you can lay down one single layer of atom and then lay down 5 more layers of atoms and then lay down one more single layer of atoms. And so you need an electron microscope. It's the only thing that has the resolution that can look at things like buried interfaces, looking at the atomic structure of materials. So that's kind of the science behind what we're doing. But why am I giving a talk at an HDF5 user conference? And so how is HDF5 used in TEM now? So at Berkeley, we have a Berkeley Electron Microscopy Dataset, or EMD file, and you can see the structure over here, which is online. And so there are several open source projects that now support this, whereas we previously, it's kind of one of the only data sets now that's open and being supported by a lot of different people. Most of the data sets are generally provided by vendors. And so the vendors have a proprietary data format. But even these detector vendors are starting to switch from their closed proprietary formats to HDF5. So Thermo Fisher makes a lot of microscopes, and they have what are called VLOX files, which are unfortunately also called EMD files. And Amatec or Gatan is their new digital micrograph 5 version is going to be HDF5 as well. And the thing is that dataset size and extra dimensionality is driving the community towards adopting these open file types. HDF5 seems like the winner, especially because we're heavily using Python through HDF5Py. And we really are pushing them to do open extensible data sets, because why is our data locked in this weird format? And then we really want access to the large overarching HDF5 ecosystem. If you write it in this format, you get access to so much stuff that's already written out there. So I'm going to specifically talk about a very large data generator that we have at LBL called the 4D camera. So the 4D camera is kind of the peak, is the top generator, one of the top generators of data in electron microscopy right now. And that's part of this exponentially increasing data rates we have in our field. So my background in TEM big data is I started kind of in 2005 working with what were big data sets back then. And it was electron tomography. So these were like less than a gigabyte a piece, but that was huge in 2005. You could barely fit that in a computer memory. So we were also taking movies at about 1 second per frame. In 2012, 2015, there was a big change in that we get these new detectors that are based on CMOS, and they can run at about a millisecond. And so we were getting tens of gigabytes of data set. And we were walking around our facility with hard drives and plugging them in, into different computers and moving them around. We got a little bit smarter. We're starting to move things with 10 gigabit, like getting better infrastructure, getting a NAS, things like that. But of course, the detector starts getting faster. So now we're running in millisecond speed. Sorry, I was talking earlier about 100 millisecond speed. Now we're in millisecond speed and hundreds of gigabyte data sets. And the data I'm going to talk about today is going at microsecond speeds, about 10 microseconds. And so that's terabytes of data that we're producing per day and in just a few minutes or seconds. So we can see this exponential increase. I started where about this red curve is. So I've worked on kind of all kinds of different types of data and data generators. And we have a new project that's coming out that's going to increase this by a factor of 10 in just a couple of years already. So the 4D camera is a CMOS active pixel sensor. It has about 10 micron pixel size, 11 microsecond readout, rolling shutter, 576 by 576 pixels, and it's 2 bytes per pixel. So that comes out at 58 gigabytes per second. And what do we do with that data, right? How do we even acquire that? We have 4 FPGA modules that the data is striped across. We have 4 receiver PCs that have 256 gigabytes of RAM that can ingest the 480 gigabit per second. And then we offload that from RAM because a full frame is not on one machine at any one time, and we need the full frame to do our analysis. We offload that onto a processing and storage PC. So our typical data set is about 650 gigabytes, and that's captured in about 15 seconds. We then offload it from the RAM that's it's acquired live onto flash storage onto this 5th PC in about 120 seconds. That's over 80 gigabit. And then we compress that down into a sparse HDF5 in about 8.5 minutes. We'd like to get this even further down. You can see how things are getting longer and longer and longer, and the user has to wait longer and longer for each one. So we'd really like to get to rapid and maybe possibly live processing. So we've started, there's a lot of open source packages for this, but StemPy is one that I'm heavily working on directly for this detector. So we're trying to do local and remote high performance computing, so edge compute, and also sending things to a high performance computer. And the whole point is that, is the data useful? When is it useful? Scientists really need minute scale reduction. So we're talking about, I want to take a data set and I want to get an answer back in a few minutes. We don't need milliseconds. We don't need seconds. A few minutes is probably good. So we'd like to improve our time to useful information, because if I know that the data set's good, I want to stop and I want to take another data set or put another sample in or do something else that would be much more efficient. Why should I take 10, 20, 30 data sets in a day and then we only use one in the end? So I just want to stop when I get that one good one. So users really just want to work on their laptops. So things want to fit in memory. You want things to be on the hard drive. Mem mapping is very nice and very easily processed, because we don't want users to be computer science experts in order to get their science out. So I have to go a little bit over the physics of how the energy is deposited in the detector so you can understand how we can make it sparse. So an electron, they scatter very strongly in materials, and previously pixels were very, very big. And in some detectors, they still are very, very big by design. But an electron at 300 kV, which is a typical accelerating voltage that we use in an electron microscope, have a lot of energy and they deposit in this pixel. They deposit in depth, but they also deposit laterally. So one way to get rid of this, well, the problem here is that if you deposit energy laterally, then that's called a point spread function. So it blurs your image, basically. In order to get rid of that, you can just thin your pixel down. One way to do it is to thin your pixel down significantly. So we're using these CMOS ICs in order to only collect charge in a very small area of the detector. And so that allows you to have very minimal blurring between pixels. But this also gives us another advantage that we can use, is that if we can run fast enough, that we can do what's called electron counting. So in a typical charge coupled detector, or CCD, the old style detector, you would have an electron would hit a phosphor, and then the CCD would actually look at the light that was produced by that electron, but you'd get this large point spread function. Even though I'd want to know that the electron hit a certain pixel, we get charge deposition all around the detector. This doesn't even take into the noise of the detector in the background. And so what your final image would be this high peak in the middle with this spread of electron energy all the way around, which gives you this blurring effect. But if we can run fast enough, or we can see single electron events, so that we can localize those events. So if we can thin the detector, run super fast, and each one electron is imaged by itself, then you can actually you can see this charge cloud energy deposition, and we can reduce all of this energy to one pixel. We can put it back to where it actually came from. And so that means your detector noise is 0, basically, and you're just counting electrons as they come in. So this is what our raw data looks like. And if you do that electron counting, you can get to just electron hits. And then we can sum infinitely, basically. We get infinite dynamic range, technically. And so if you just sum 300 frames, then you get the image of the object, or this is a diffraction pattern that you actually wanted to look at. And so this 1% fill factor and running super fast at about 11 microseconds per frame, we can get about 3,300 electrons per frame because we can localize each one. And then if we do that in a sparse way, once we reduce that data, we go from about 650 gigabytes down to much less than 20 gigabytes, usually in the range of 1 to 5, but you can get a massive reduction in scale. The only problem is, where's the sparsity? HDF5 doesn't have a native sparse data type. So in numerical analysis, scientific computing and sparse matrix or sparse arrays, a matrix in which most of the elements are 0. Our previous speaker just talked about this. 90% of their data is basically 0. So having a sparse ability would be really nice. So HDF5 is very popular open source, as we all know, and it's developed primarily by teams at Berkeley Labs. So it's very widely used. So being able to get sparse data into an HDF5 format would open it up to a huge ecosystem rather than needing to write code that understands the sparse data that we're fitting into it. So here we're using, for the 4D camera, we're using a linearly encoded sparse data representation, where we can imagine a 3x3 image where we have just 3 electron hits. And so you can say that 0, 2, 1, 1, and 2, 2 have an electron, and the rest of them don't. They're 0, so we don't even care about them. We just assume they're 0. So we can also say that pixels 0, 1, 2, 3, 4, 5, 6, 7. So 2, 4, and 7 have electrons in them. So this, though, gives us this sparse ragged array because every frame sees a different number of electrons based on the way that the electrons scatter and they come out of the source. So we had to use this ragged array in HDF5. So luckily, HDF5 allows you to have one dimension that is not always the same size, but that's only one dimension that we can have. There's lots of different ways to do sparse arrays. And then the problem is that we have to write our own code, or we have to give people special code in order to understand that sparse format. They can't just work on it like independently. They can't just use it like a dense array. So we have to take this ragged array. We have to have something in between that goes sparse to dense, and we get our image out in the end. So what we really like is if we can store it sparse, we like 2 ways of looking at the data. HDF5 would return this normal dense array, where this is a very, very efficient array that gives you back this dense data. So it's very transparent to the user and upstream packages, because we have a lot of data sets and we have a lot of processing that is already written, but it does not understand this type of sparse data. You can slice and operate on it like a normal array, and it would do lazy loading. So you only compute what you need when you need it. You can leave the sparse data either in memory or on disk. And then if you need a frame, then it blows that frame up, and then you operate on that frame and then throw it away. Otherwise, you have to load all 650 gigabytes of the data set. So then the other thing is that there are also algorithms, though, that you can put in the sparse domain. So here we have this paper that is on arXiv and is coming out recently, very soon. And so you can do binning or cropping, center of mass, radial sum all frames. And if you use the dense format or the linear index encoding or run length encoding, you can get different speeds for these algorithms, massive speed ups in the speed. So you want to be able to get a dense array out of HDF5, but you also want to be able to access the sparse array so that you can implement very efficient algorithms in the sparse domain as well. So we're not the only people doing this. The previous speaker just talked about this, but there's extreme scale sparsity coming down the road very soon. Our detector is not the only one. We're going to have one that's 10 times faster and still sparse in the future. There's significant, there's already detectors that would benefit from this, and there's many more detectors coming online that are going to benefit from this. So our 4D camera, we have a sparsity of greater than 100x. There's SLAC LCS2. The 4D camera was kind of seen as a test case for LCS2. They're going to have the same thing. They're taking frames and they're going to be highly sparse. There's many different experiments that need a solution that enables all users of sparse data to benefit. So I'd like to just acknowledge the 4D camera team and my collaborators who have done a lot of work on this. We've worked with Kitware very, very well to do a lot of this processing. They've accelerated a lot of the work that we've done. We would still be working on data sets that we took 2 years ago if it wasn't for them. We're just scientists, but we need people to run the algorithms quickly for us. And this increase in data output is only going to accelerate, so it's getting worse. So with that, I'll take any questions that anyone has. Thanks.
Thank you. Any questions? Elena, you...
No, just comment. We very well aware of the problem. We worked on the project with Soren, prototyping solutions. We know how to do it. So we are looking for funding to implement it. It's not an easy effort, but all requirements that you listed here can be addressed. So wish us luck.
It can be done. The problem is we can't get funding for it either. Everyone says, no, somebody else should fund this. This doesn't make any sense. Why isn't this done? Just do it. That's what everyone says.
But we're aware and we'll see what we can do. But you're absolutely right. It's the problem that is everywhere where you look at high energy physics. Mark Paterno may address this too. In bioinformatics everywhere, right? And in many X-ray and neutron scattering detectors, they have exactly the same problem. They're using special compressions to deal with data, but with the new rates, they're facing the same issue. Yes.
Peter, I was going to ask about compression. I mean, is that a stopgap solution in lieu of a native sparse format?
I think it is. So I have tried it. So we are thinking about doing compression, but a lot of times the problem with that is you always have to blow it up into the dense format. So you can't operate on it in the sparse domain. We get humongous speedups by looking at things in the sparse domain. So like for instance, our 650 gigabyte dataset can't fit on a GPU, and getting that data onto the GPU is hard. But if it's only a gigabyte instead of 650 gigabytes, we can operate on it in the GPU. It fits in memory. You can blow up what you want, operate on it, you're done. Like it's super fast. So that's where compression doesn't really help. Doesn't really help us.
Right.
And what's the problem? Just kind of like an application level sparse structure. I mean, where is your application understands the sparse storage layout, and you just write that encoding.
Yep.
Okay.
Yeah, they have to have custom solution every time, right? And
Yep.
each of instrument developers, they have their own custom solutions. So it's completely no interoperability between data and software. So it's silos that we're facing again.
So we're going to go back. We've just gotten the vendors to allow, like, to open things up, and they're all going to go back to this. If they're all going to, if it's going to go sparse, they're all going to make their own implementation, and it's going to be, anyway, they're going to be inefficient. Nobody can work on the problem all together. And we have a whole bunch of already existing open source programs like Pi40 STEM, like NSymPy, HyperSpy. There's significantly more. And if these, we have to rewrite these entire packages for sparse data.
No, addressing it in HDF5 is a win for everyone. So we need to pursue.
Hi, I have just a comment. Well, actually two comments. First, this was an amazing presentation. Thank you so much.
Thank you.
You were just mentioning that there is this problem in which applications don't understand the format of sparse data. They are probably aware of how to parse a matrix-like grid, right? So there is a talk I'm gonna give tomorrow morning on what I'm calling user-defined functions for HDF5. So the idea is that you can pretty much embed your own logic for example, convert sparse data into a grid-like format, and the application just reads that function. So basically, when the application reads that data set, we invoke the function that on the fly translates the data from sparse to a layout that the application knows how to parse. So maybe that's a prototype that you can look into to see if it helps, and then eventually move down such an implementation to a vol connector or something that's more performant. But yeah, this is it just popped up that this could be an interesting use case for UDFs.
Great.
Yeah, that's a good pointer for this.
I have a question about parallel I/O. Data in the dense format that is easy to divide among multiple processes, just using data lengths along different dimensions. But if it's in the condensed format, how did you decide the range of the data to be read by each individual process? Is it easy way to do the calculation, but not reading the real data?
For us, generally, in almost all of these detectors, you can think of them as every frame of the detector is pretty much independent. That's our goal, at least in a lot of cases. So for these sparse arrays, each one of these parts of the ragged array, I can just break it up in terms of every single one of these. I can just look at independently. So if I want to operate on one frame, which is what I normally want to do, then I just need to break it up in terms of each one of these parts of the ragged array. So if you wanted to break it up into there are a lot of things that are multi-dimensional. So that's beyond my knowledge or capability. So being able to slice into a multi-dimensional sparse array would also be, I think, very useful. Not as useful for us, I think, though.
Okay, let me use this example in your slide here on the lower right corner. You have a multiple ragged array here. If I have, like, say, two processes, I want to read all this data because each row is of different size. How do I know if I want to balance the workload among these two processes? How do I know the length of each array so I can pre-calculate this how many rows that each process should read?
They're all going to be fairly similar. They're not going to be like different by major factors. To the electron microscope, for us, it outputs a certain number of electrons per 11 microseconds. And so you kind of understand how big they're going to be. The standard deviation of the size of that is not humongous.
So your suggestion is just evenly divide the row among the process.
Yeah, we would just equally divide them, but otherwise you'd need some other load balancing or some other technique for that. Yeah.
All right, thanks.
Okay. All right, cool. Thank you. And yeah, I think we are slightly going into the next talk. All right. Thank you so much, Peter.